So for completeness sake, couple of things which were missing. By the way, your exam or whatever midterm or homework or whatever it is done. I have to just type it and I'll upload it. I'm not just getting time. I'll do it. I know you are happy with that, but I'll do that essentially. Okay. Yeah. So there are a couple of things which I need to mention. Uh, so before going back to the Higgs, if you remember the Higgs potential, this is in the unbroken phase, right? Now, typically, you keep hearing the statements that the symmetry is restored, right? When is the symmetry restored? When is the symmetry restored? If it is just running by energy, it is restored, or you need something else to restore it, essentially. You need density. So, what happens is the electroweak symmetry is restored only after higher temperature effects are controlled. So, you have to write an effective theory, finite temperature field theory. So, then we have to write V of H at finite temperature, and then you can show that this temperature is restored. The wave becomes zero. So there is a temperature at which the wave can become zero. So now when you do a finite temperature effective field theory, you can calculate these corrections essentially. These corrections have a particular form. There are some field dependent mass terms, very much similar to trace square by log m square by q square. Okay, all of them are field dependent mass terms, very much similar to Coleman-Weinberg. And then when you minimize this, you get a potential wave which is called V of t. Okay, V of t. This is the minima at a given finite temperature. So now you can ask the question, when does the electroweak symmetry is completely restored? When the V of t becomes completely zero? Roughly around 10 power 12. So there is a range of, depending upon the parameters or something, and so between say 1 TeV and 10 power 12 GeV, okay, the symmetry is completely restored. Okay, you can actually show restoration of electroweak symmetry symmetry under finite temperature. Now, why I am saying this? Because typically what we use say is that when we go to high energies, okay, when we go to high energies, the potential will become negative, and so it becomes completely unstable and so on. So it is true. It is true, but we are not looking at a spontaneous symmetry breaking at high energies. The coupling values will change everything, but you have to think when the symmetry is completely restored only at finite temperature. The Higgs may become unstable and so on. So the potential may become unstable. So there are these famous papers by Sanjanovic. 1 second, I'll just come. Sanjanovic. Mohapatra. But you can read all of about it in Kapusta finite temperature field theory. Kapusta. This is not exact. I'm not sure. This is just formally I have written essentially. It is some field dependent mass square term, depending, and then there is a trace log. It looks very much similar to the Coleman-Weinberg. Okay, it looks very much similar to, but I'm not sure exactly the form actually. Now, okay, this is trace of the mass matrix. It depends upon the eigenvalues, some of the eigenvalues. In supersymmetric theories, this is replaced by supertrace. Okay, so yeah. So spontaneous symmetry breaking is a collective phenomena. So you need many particles. So bosons are many particles. They combine and then when they go, they all settle down at a finite value in the potential. With the potential, if it has some shape, essentially, they settle down at a place which is away from zero. That's the crucial thing. Okay, that is, they settle down at something which is away from zero, very far away. Okay, they settle down at some place. This inverted M shape of shape. Now this is a collective phenomenon. Now, what exactly happens when symmetry is broken is that because you form a condensate essentially, so it's like many particles of Higgs are settling down, and they are at the lowest energy state possible. They are almost like a classical field, a constant classical field. So they all take the same value. Now, if you want to restore this symmetry, okay, it's not just sufficient that you start measuring the Higgs couplings at higher and higher values. Okay, at higher and higher values, what happens? This shape keeps changing. Okay, the shape of the potential keeps changing. Okay, and at some point it just becomes like this, and at some point it may also become like this. When lambda becomes negative, it may also become like this. Okay, at some point it may become, when lambda is very very close to 0 or something, okay, it may become like this. But does it mean that the symmetry is restored? No. That's the point I'm making. There is a huge difference between the potential being unstable and the symmetry is fully restored. Symmetry, suppose if you have a collider sitting at 10 power 11 GeV and you measure the Higgs couplings at that scale essentially. Okay, the Higgs couplings are modified essentially. Higgs couplings are modified. Okay, but in the collider, you may measure the Higgs coupling you measured, but at the collider, do you really see the broken phase? Not really, because you are not producing a condensate. You are not putting a, okay, you are not producing a condensate essentially. Okay, instead, in the early universe, after the Big Bang, okay, after the Big Bang, before the, say, Big Bang nucleosynthesis or any of the, okay, before even the QCD phase transition, there is the electroweak phase transition. Because it's a dense ball of gas essentially which is moving around. So the symmetry is restored in the early universe. So there is an unbroken phase in the early universe, and when the universe cools down, okay, the electroweak symmetry is explicitly broken down. Okay. Now, why this is important? Essentially, I am telling you the finite temperature corrections are always important if you want to have. We had the electroweak baryogenesis, right? Essentially, in those cases, what happens is the vacuum to vacuum transitions during the electroweak phase transition are enhanced very strongly with the temperature. Okay, some of these vacuum to vacuum transitions are B and L violating. Okay, B and L violating, but with finite temperature, the transitions become very fast, very large. So the electroweak phase transition is a very important aspect. So it can play a role in, say, generating B and L violating interactions and everything. That's the idea, right? Essentially, the basic idea is that we want to measure the lambda in all the experiments. So we don't know. So as of now, we don't know the unbroken phase. That's the theory. We cannot study it, except that we know that it happens in the early universe. And the standard Big Bang cosmology doesn't even touch that because it starts with essentially 1 MeV around that scale, essentially. Except if you are doing the baryogenesis or leptogenesis, you don't touch those scales, energy scales, in cosmology. Okay, so 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 this is the difference between temperature and energy. So what happens with energy? So to study this, people start writing the RG equations of lambda. Okay, start writing the RG equations of lambda. Lambda crucially depends on two parameters. It is the anomalous dimensions. So if there are couplings, this we call it as beta of G3. Okay. So this is, I said, this is a beta function. This is typically called as anomalous dimension. Okay. Anything other than the gauge couplings is called an anomalous dimension. Echo couplings, lambda couplings, everything are called anomalous dimensions. So the anomalous dimensions are typically represented by Y or by lambdas, or depending upon the place. So Y lambda goes at third power of theta plus Y T Y. So the main thing which couples to, so we'll see. So we need 4 Higgses. Okay. This is a dominant one which goes with a minus sign. Okay. There are 4 tops. Okay. So that when you integrate the tops, you get the lambda coupling. Similarly, you have RG equations corresponding to okay self energies of the lambdas. So you can have lambda square, lambda square, lambda square. So you can have RG equations proportional to lambda square essentially. So each one of them is separate diagram. Okay, I put it everything there. Then in addition, you cannot also add a higher order diagram, but this is at higher loops. This is at higher loops essentially. This is also possible. These at higher loops. Okay, the lowest order you can have is lambda square. I think I'll just check it. Can somebody dig out this paper? I thought I brought that paper, but I didn't bring. I brought effective field theories. Okay, the paper of okay. Anyway, now these things, these RG equations were known up to 2 loops and dominant 3 loop. Now, how will you solve this RG equation? This one or this one? This one. So this is one diagram, no? Self energy. This won't be absorbed in mu. This is 4 lambdas, right? Some parts will be absorbed in mu, some parts will be absorbed in lambda. Right? Yeah. Yeah. Depends on which one you want to say. So this is just lambda square, right? Now, these plus all the parameters of Standard model are coupled. So when you want to solve this equation, one loop, it was this exercise was started in the late 80s. Altarelli, Italian group, Sudhir, all these people started, and Mayani and company. They started this thing. What they are worried about is 2 features of the Higgs. See, lambda 5-4 theory has a lot of interesting field theory properties. It has a one-to-one correspondence to Ising models in various dimensions and everything. Okay, so it can, if you put in okay, so lambda 5-4 is very well interesting even in condensed matter-like systems and stuff like that, StatMech and everything. So they were interested in 2 things. One is the trivial bound. If you don't know what is the Higgs mass, you can ask what is the Higgs mass when which lambda Higgs equals to 0. Okay, due to running. And then non-perturbativity. Lambda becomes infinite. That means it just becomes too large, greater than 16 pi square. So for us, anything which becomes very large. So are there any parameter ranges? Okay, remember when they started this program, they didn't know what is the Higgs mass, they didn't know what is the top mass, they didn't know anything essentially. Okay, third one, stability. does lambda become negative due to radiative correction at some scale in energy, in the running of the parameter. Now, in some sense, with the Higgs mass discovery, these two don't play a role anymore. We know that Higgs mass is 125 JeV. Okay, these two don't really play a role essentially. So these are only for historical purposes. You can look at Higgs Hunter's Guide or okay, anatomy. He has 2 volumes, 2 physics reports. Abdullah Jawadi. And there is also one more thing, which is you can read it in original paper, also in Higgs Hunter's Guide. So after the Higgs has been discovered, because I know the mass very precisely, the question of stability can be studied very precisely with the most accurate measurement possible, essentially with the most accurate theoretical apparatus we have. Now the point is, when you solve these equations, these are differential equations, coupled differential equations, they need a boundary condition. So what is the boundary condition you choose? You choose a boundary condition to be the left boundary condition. Okay, and the differential equations are written in particular scheme. So they are always written in the renormalization scheme of MS bar. So all these differential equations are written in MS bar scheme. Now you want to extract all the parameters, MS bar parameters, match it with experiment. Match it with experiment. So when you match it with experiment, if you are using say 1 loop RG equations, the matching is tree level, the boundary condition matching. If you are using 2 loop RG equations, you have to use 1 loop matching conditions. Okay, and if you are using 3 loop RG equations, you have to use 2 loop matching conditions. And these matching conditions were not known until recently in the standard model. Like I said, people have not done the full MS bar renormalization of all the parameters of the standard model, okay, at all levels, at 2 loop level. So part by part are known essentially. So these matching conditions, especially Melnico and company, they have done it essentially. All these formulas were collected recently and put it in a very nice analytical form. Okay, very nice usable analytical form. Okay, now this was done by I'll show you the slides Thursday anyway. This was done by so one of the first things people did was they collected all these formulas and everything. What they found was lambda becomes negative at a scale 10 per 11 J. Now people said, okay, we should not consider this very seriously. That means it's not stable, first of all. Okay, with the latest thing, you can show that it becomes negative around 10 power 11 G. So the moment lambda becomes negative, the potential just becomes lambda square plus this thing. Okay, it is unstable essentially. Okay, and at higher ranges, if you really push it very hard, it can become inverted also in principle essentially. Okay, lambda becomes negative at 10 power 11 J. So this led to a lot of new physics indication for new physics. This was considered as a indication for new physics around 10 power 11. This was with the Higgs mass 125 J. With the Higgs mass, so what were the new physics models which were considered at that time? That was the most popular thing to consider, something called so all the type 1, type 2, type 3 seesaws were considered essentially, such that the entire question they asked is somehow you have to make this positive all the way up to the Planck scale. So the Higgs should be stable, meaning the Higgs potential should be stable all the way up to the Planck scale, otherwise it's an indication for new physics. Now I said that these threshold corrections or these matching conditions for these dynamodal parameters were known recently only at 2 loop level, right? So using all those formulas, okay, what people found was that, and using the uncertainty in the Higgs mass and the uncertainty in the top mass, okay, this Giudice et al. Found was that it actually surpasses 10 power 11. Okay, if you use the uncertainties and everything, it becomes scratches almost touching 0. Around the scale 10 power 18. Okay. So almost touching 0. It is not exactly negative at 10 power 11. If you add all the radiative corrections and everything properly, essentially, and you say it's almost touching to 0. But what they mentioned was that one of the biggest thing what they did was they computed the lifetime of the vacuum. So if a given state, okay, so what they said was when it goes like this, okay, the potential will have some corrections, right, essentially. So lambda will be like this. Okay, you compute the potential and find out its minimum energy, and you calculate if there is a deeper minima somewhere nearby. You calculate if there is a somewhere nearby, there is a deeper minima, and you say if there is a deeper minima, it decays into that minima. It could be unstable, that minima could be unstable, but the deeper But this minima could also be extremely long lived. So such minima are called metastable minima. That means they have a lifetime which is greater than the universe, age of the universe, and they take a they are not the true minima, they are not the true vacuum, but they are vacuum which have very long lifetimes. So to calculate this thing, normally people use Cosmo transitions and various things, these lifetimes essentially. Okay, these calculations. But now there are some slight analytical methods which you can use. So you have to use the compute what is something called the Euclidean action. So okay, and then the bounds solution essentially. Okay, and then you can compute the lifetime of this particular vacuum essentially. This was first done by Coleman and DeLucia and company essentially. That was the reason why I wrote their names there essentially. So the lifetime of the vacuum, if it is long lived, okay, if it is very very long, it is called metastable. I am coming. Then there is stable minima. This is the deepest vacuum or the true vacuum. Unstable minima, that means lifetime less than tau universe. The lifetime depends upon the mainly depends on two parameters, the Higgs mass and the top mass. It depends on the Euclidean action and everything, but the only freedom we have, because everything else is fixed, the only freedom we have is the Higgs mass and the top mass. A structure of the problem, that's it. So if the potential is like this, like this, like this, like this, like this, like this. So after adding radiative corrections at every point essentially. So you will calculate if there is this minima to this minima, this minima to this minima, this minima. Some of this minima could be very, very long lived. So what they found is that, I'll show you the graph Thursday. In empty MH plane, there is an ellipse like this, okay, which the experimental numbers are like this, preferring metastable so the present experimental numbers seem to be preferring that we are living a universe with metastable minima. Okay, and now this led to, how do you explain this? Okay, we are living in a metastable minima very very close to lambda is equal to close to 0 essentially, without assuming there are no new physics. There is no new physics, only the standard model. It is greater than the, but it's not the true minima. So metastable means it is not the true minima, but it's long lived. How long lived means it should be tau should be greater than tau universe. Okay, not true minima. Okay, good. It's good. We don't have to worry about it. If it is stable, then we don't have to worry about it. It is the deepest minima possible. No, 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 no BSM. Pure standard model, RG running, okay, but two loop, three loop RG equations, two loop matching conditions, full two loop matching conditions. Um, Meaning they show that it becomes stable. So because the corrections don't seem to be modified much, for loop order will not be modifying much. They are much smaller, so it sort of stabilizes essentially. Okay, so this led to a lot of speculations. Again, like I said, speculation, power, speculation, speculation, power, speculation, sort of thing. So this led to a lot of speculations, which will come um, uh, later on. Essentially, some of the speculations. But one of the first speculations is how to fit it in something called a landscape. So they say that this is the evidence for a multi-universe or landscape. So you have multiple universes essentially, each with its own different set of parameters of vacuum expectation values. Okay, the vacuum expectation value sets all the couplings and everything essentially. Okay, all the parameters. Somehow the universe is adjusting within all these multiple universes a region which the question is it is a critical region essentially. Okay, you can put it. So lambda 54 is a critical theory essentially. So criticality you can measure it. Okay, so you can equate it to some statistical mechanical models like sand piles and something, and then you can play around the same thing on a landscape. Okay, okay, that there is a landscape, and within the landscape only those vacua which satisfy these conditions are the stable and uh, what do you call okay. Now the question is, because now you say that there is a statistics of universes which are born and only some of them are stable, some of them are critical. Essentially they are like how the sand pile is critically stable essentially. In the same fashion, you, because you have a lot of universes, only some of them are critical essentially, satisfy the criticality conditions. Now the question is there some self-organization principle beyond all this? So is there a self-organized criticality instead of God putting all these universes in such nice heap or something essentially, but some self-organized criticality? So that is the direction this is going in essentially. It's almost like statistical mechanics of universe, and how do you put write down the equations, statistical equations and everything essentially. I won't discuss this, but this is one kind of physics beyond standard model which you can work with if you are interested without having any new physics, and which is not the approach of effective field theories. Okay, so the entire claim of these people is that SM is critical in the statistical mechanical sense, critical parameters essentially. So there are these powers which are, you can exponents of you can write them in terms of exponents, that there is like a phase transition. It's critical, and so you can map the entire thing to something called a landscape. Now it also happened around the same time there was a landscape from string theory which came up essentially, so they could connect to the string theory landscape. String theory landscape came around 2003 2004, but it really became popular much later on essentially. all these couplings are energy dependent, right? Because renormalization makes them energy dependent. Uh, a good point. That what we so you yeah, depends on the scale. Yeah. So at those scales, when it becomes unstable, so you can ask the question whether it's stable all through the universe. That means all through the age of the universe at all energy scales or not, or is it stable, unstable at some energy scales. So if so, what are the consequences? Whether the universe is stable, meaning decaying in those kind. So those energies, the universe may decay. So it will have impact. It will have a landscape of this thing. Okay. So that many fraction of universes will decay faster. Okay. So it becomes. It depends upon the energy scale at which they are distributed. It depends on the distribution at each energy scale. Our universe will itself decay, no? Because the decay rate is proportional to the energy. Okay, the decay rate will be proportional to the energy exponentially, exponentially power minus something. So if the energy is very large, the decay rate will be very slow. The question is eventually whether it's stable or not. But at finite temperature, this will increase. Okay. So if it is 10 power minus m Planck or something, it's a very small number. So it decay rate. Okay, so it's slowly decaying wherever the scale of unstability is. If it's 10 power 11, so it's decaying slightly faster because it's exponential. I wanted to talk more about this, but yeah, I won't talk. Okay, I can talk about KKLT and all the landscape and everything, but yeah, I won't talk. But you realize the difference between metastable, stable, and unstable minimum, right? Essentially, unstable means its lifetime is less than the age of the universe. Metastable is lifetime is greater than the age of the universe, and stable means it's the deepest minimum, the truth minimum. So landscape again says that okay, it's you don't care about hierarchy problem, you don't care about, so it converts the problem into a statistical mechanics problem essentially. The entire thing just becomes some statistical distribution of universes and change of parameters, and this eventually uses some sort of anthropic arguments essentially. But people are now saying that it's not anthropic, because anthropic in the sense that uh, there are these bounds derived by Agrawal and company and also by Weinberg, that you cannot have any wave value in any universe. So the wave value should be very precise such that otherwise galaxies won't form. So I think in 87 or something, Weinberg wrote a paper on the anthropic. It's a very interesting paper. Now the Higgs wave also contributes to the proton, neutron masses, everything. It sets all the fundamental parameters of the universe. So the implications of the Higgs wave on various fundamental parameters at a nuclear physics level and atomic physics level were studied by Agrawal and company. Barr, Agrawal, several people, for 4 others. What they did show that the range of wave which is allowed so that we have a stable universe in which there are galaxies which are formed and everything is extremely precise. So the wave cannot get modified significantly, not even by 2% or 3%. So the delta V, I think, if I remember correctly, 2 to 3%. I think this is, we need to check. I don't remember, but it's very strongly constrained from atomic physics and nuclear physics, and from astrophysics. Weinberg showed that you cannot form galaxies, okay, with when the Higgs is, wave is modified significantly. So he put a very broad range of bounds, and then these bounds were really redone by these people by putting into consideration nuclear and atomic physics. Saying that the wave takes the value so that we all survive. That is the anthropic argument. Okay, the anthropic argument is that parameters take those values so that they support life. The parameters have to take the values they have to such that they support life. Okay, that is the argument of anthropic principle. But now if you put the same arguments in a landscape, now it looks like a statistical thing essentially. It gets converted into criticality. Why these values become so critical such that, or if there is a phase transition somewhere there, so such that then you tie it up such that only this particular universe is surviving. Okay, so this entire thing becomes a statistical argument in landscape. Now from string theory side, I'll just mention, what time is it now essentially? 12:30. Okay, I'll just take 5 minutes and I'll stop this. Okay, another, I just mentioned why this is popular. In string theory side, you all know superstring theory lives in 10 dimensions. Okay, so there are these 5 string models. This is called M theory in 11 dimensions. These are old stuff. Nowadays, nobody does this anyway. It's for 32. There are this something called the 5 string theory. People believed it's in 10 dimensions. Now you have 4 dimensions only in universe. So there are remaining 6 dimensions. So you can write the potential, the space as ds square is equal to ds square 4 dimensions times m6, where m6 is the compact dimension. So when you make this compact dimension, what happens is, like I told you, if you have a compact dimension, like I said in extra dimensions, essentially there is an extra dimension. So there is a compact dimension. This radius will not be stable because the branes will start moving. Okay, the radius, because under gravity the radius will not be stable number. So you have to do stabilization of this radius. So if you this M6 means there are 6 dimensions, but the number of possible dimensions are very large. So there are depending upon something called, these are called complex moduli, depending upon how you compactify. So one particular case is type 2b compactified on Calabi-Yau manifold. So it's a manifold, it's a complex manifold essentially. It's I said I won't talk about it, but I'm talking. I couldn't stop myself. But anyway, yeah. So Calabi-Yau manifold, which compactifies, and there are several what do you call moduli associated with it. Okay, because it's a complex space essentially. There are a system of Diophantine equations and all. Now the point is that are these all these moduli or this radius moduli are these radius essentially are stable or not? People thought that for a long time that there will be only one stable configuration. There will be only one stable configuration which leads to the standard model. String theory will have a unique solution. Okay, that was a thought. But then what they discovered was that just like you can put branes, you can put fluxes in these extra dimensions. Okay, and these fluxes will stabilize this vacua. Okay, when they stabilize this vacua, it has been shown by various people, including Bucco and Witten and company, essentially, that a particular configuration, because all the string theories are same, they are different expansions. In a particular configuration, all the moduli are stabilized. All the moduli are stabilized, and there are 10 power 500 such possible configurations possible. So instead of one, you ended up with that counting itself is a the counting itself was done by several people. Okay, and there are papers like your counting is wrong, my counting is correct, and so on. So okay, and most people are Denef and Douglas who did this counting essentially roughly. So there are approximately, you can count it because it's all number of configurations possible and everything. Okay, you can estimate it. These are not explicit counting. Okay, so you suddenly have 10 power 500 vacua possible from string theory. Okay, so these are all called flux vacua in type 2b. That was first. Okay, and then they questioned that okay, string theory doesn't support de Sitter vacua. De Sitter vacua are essentially vacua in which there is a positive cosmological constant. Okay, and so the discovery of the cosmological constant was considered to be anti-string theory. Okay, so string theory doesn't have cosmological because it cannot support de Sitter vacua. It cannot support vacua with a positive cosmological constant. Now you have seen what they have shown, what KKLT have shown is DS vacua in string theory 10 power 500 of them. Okay. All of them were de Sitter vacua. Okay, and they constructed explicitly. Okay, they constructed explicitly all this vacua and showed that there is a landscape of vacua possible. For a long time, people started arguing, counter arguing, and everything, but it took some time to sink in. But people accept that this is correct, except for the details. Okay, whether explicitly one vacuum is fixed or whether there is fine tuning, no fine tuning, all these kind of questions you can ask essentially. But at the end of the day, this is true that you have huge number of flux vacui from string theory. So now, which one will have standard? Which one will have standard model? And all the parameters will run, take different values in all this 10 power 500 value vacuum. Okay, so all the parameters will take different values in all this 10 power 500, because in string theory all the couplings are determined by some field taking vacuum expectation value. So okay, so all the parameters will take different values. So the point was that suppose if you go do that, you have a string landscape. You have something called a string landscape. Disappear. Now people, this is it, one particular string theory which can be computed and everything understood. Earlier people were trying to do from SO32 or E8 cross E8, because then from SO32 you can go to a standard meaning grand unified theory, okay, SO10 and so on. So from E8 cross E8 they took as one of the E8s as a hidden sector, one of the sectors as a visible sector. So there is a mirror symmetry. Okay, so that's how they, so all the mirror models were based on E8 cross E8 sort of symmetries. Some of them, or E7 or something, and derivatives of them. Yeah, there are anti-decision resolutions are possible. De Sitter was a problem. It was a problem, but now they show that you can construct De Sitter solutions with concrete, with all the moduli stabilized. You can construct such vacuum solutions. And how many of them you can construct? Okay, all right. But then, of course, string theory is the only theory which we know which works very well at Planck scale. We don't want to give up on it. So so we want to make sense of the string landscape and see if we can make some calculations on it. So that's the basic idea of connecting this with the metastability of the standard model. Okay. String theory contains gravity. Ten dimensions, superstring theory. 10 dimensions superstring theory. Okay, so the metastability of the standard model is connected with the string landscape, and so you can complete the picture. So what was originally thought that there will be a grand unified theory and then there is a string theory and everything, that entire program got cancelled, sort of got modified into a string landscape essentially. And the claim that there is a metastability, what we are living is a metastable universe, can be mapped into a string landscape. Okay. Okay. So okay, and now okay, I'll stop here, and then I will start with positivity and unitarity constraints and effective. I'll go back to effective field theories. Okay, on Thursday essentially. I'll go back to effective field theories. Today I'll stop here essentially, and matching conditions and everything. I want to do that. I brought the Manohar's Bible here with me. Okay. but I realized that I didn't do anything about the spontaneous symmetry breaking and everything. So I did a part of the lens, spontaneous symmetry. Now, if you have any questions or any topic which you want me to cover, you let me know. Okay, I will do that. Okay, so what is the time now? Actually?